All right, this is physics 1102, spring 2023. It's exam 4 review on chapters 23, which is on geometric optics. So this includes lenses, chapter 24, wave nature of light. All right, so again, like diffraction. And then chapter 25, which is on optical instruments. Okay, so I'll go, and this will be briefly like telescopes, cameras, briefly. Not a whole lot on here. Also deal with the idea of telescopes and the idea of resolution. You know, the fact that any size telescope will not infinitely resolve an image because of the wave nature of light. We also have labs. Lab 9 is intensity and polarization. Lab 10 is on 9A, I should say. 9A, because rather than changing the other lab numbers, I figured just insert this diffraction. An interference lab. And then lab 10, which is on lenses. Okay. So, yeah, 9. Anyway, so that's what the exam is. It'll be approximately 15 multiple choice and about 5 problems. And you'll see when it comes up, you'll get the 1 attempt, and then I'll grade it after the fact. All right, so that's the exam as far as the topics and labs covering it. As far as, I'll go through the topics briefly. Okay. So, so for chapter 23, all right, ray model of light. Basically, if you have a light you think of as a ray, bounces off a surface. The angle of incidence we defined as that. The angle of reflection or refraction, depending on what we're doing, comes all perpendicular to our normals as a surface again. So we deal with it light as a particle, like almost an object bouncing off the surface, and we use the ray model for that object. Okay. We're not going to do anything on mirrors per se. I mean, the test is primarily going to be on lenses and such. All right. I mean, we'll get into mirrors when we talk about telescopes, but when we talk about light, a convex mirror, so this is convex, meaning the curvature is towards in this direction. So this would be R. Concave, the direction of curvature is in the other, towards the source coming in. So this is a concave mirror. And we'll see when we talk about telescopes, is a concave mirror is what's used for telescope, because the light comes in and then bounces back into one point, right? So that's what we're going to be dealing with there. Okay, so I'm not going to get, again, the mirrors are interesting, but they get kind of complicated as far as that's concerned. So we're not going to have really any questions on that. Index refraction. Refraction. Again, N is the speed of light divided by the speed of the light inside. So this is the speed of light in a vacuum. Again, 3 times 10 to the 8th meters per second. This is the speed inside the glass or object. So if it's 2 times 10 to the 8th meters per second, the index refraction would be 1.5. All right. So again, you have the various elements that have index refraction. And we talked about some of those before. So that's the table there if you need those numbers. All right. All right. And then from there, we have Snell's law. And that is, we have light coming in. This is air, and this is glass. Comes in, it'll be bent towards the perpendicular. So this is theta I, again, theta R, and sine N1 sine theta incident equals N2 sine theta of the refracted glass. So this is N, this is 1, this is 2. All right, so that's what we call Snell's law of refraction. Again, we've talked about that. Total internal reflection. So total internal reflection, not refraction. If we're going from basically the way around, from say glass to air, all right? Again, we've talked about that. The light bends away. We bend it enough of an angle, then it will actually just not, it will just be totally reflected. And this angle we call the critical angle, theta, is sine theta critical is N2 over N1. I'm going to use the same. So this would be 1, and this is 2, where we have N1 is greater than N2. So this would be glass to air, water to air, and so on. So this has to be less than 1, because the sign of it doesn't make any sense. This is impossible for anything else. So this is total internal reflection. This is the principle of fiber optics. It's also the principle of the sparkle of a diamond. Again, diamond has one of the highest index refractions at 2.42, and so on. So the colors are such like that. All right, so that's the first part. We get into the next part of lenses. All right, and so you have a thin lens. And we first of all have to find the focal length of the lens. So light coming from a long distance, the focal length, F, is this distance, right? From the lens to where the light comes to a point. All right, that's what we defined as a focal length. We've defined also the power of a lens is 1 over the focal length, and that'll be in meters, inverse meters. All right, so I'll call it, and this is usually in diopters, I should say. So, yep. So they call 1 diopter, so this is a diopter. So lens optometrists use this quite a bit. So that part. All right, thin lens equation. So we have a lens, we have an object, produces an image, an inverted image, again, and I'm using the same, I'm using P and Q because I don't have to have subscript. Again, P is equivalent to D object, Q is a different distance image. So I use P and Q because I don't have to deal with subscripts. And then 1 over P plus 1 over Q is 1 over F. So it's the same terms I use for the lab. And then this is the image height. And this is the object height. And the magnification is minus HI over HO because the image is inverted. So, which is also related, the same as minus, well, I should say this is plus because the image actually is minus Q over P. So the ratio of the image distance to the object distance gives us also the magnification. All right. Again, this is if F is greater than that. If P is Q is in front, that's a negative image distance. We did the lab where we had the 2 lenses and how the image of the first lens becomes the object for the second lens and so on. And that's how you can calculate for multiple lenses. All right, we got into combinations of lenses. You know, that was, I really don't have lab exam on that. We don't really cover combinations of lenses. It gets a little complicated. That's why I have it just in the lab itself. So combinations of lenses are not on the exam. So that's chapter 23. So moving on to 24. So again, we'll just be doing single lenses for the lab. And again, when we talk about lens, this is a convex. So F is greater than 0. If we do this way, concave, where we have lens thinner in the middle, this is concave, and F is less than 0. All right, so for the wave nature of light, chapter 24. All right, we talked about, I'm not going to get into this, wave nature of light was discovered by Huygens. If light coming in at one point, it spreads out as a wave through diffraction. We call this the slit width here. The narrower the slit, the more spread out the diffraction is. This is what we call diffraction. Right? And with that, we have let's do. All right, so interference, we talked about two sources, a distance d apart will produce constructive interference. This is angle, this is center, this is up here. Talked about that d sine theta is m lambda, where again, lambda is the wavelength of light. This is m equals 0, m equals 1, 2, and so on. So we get a bright spot, bright spot, bright spot, so on, when this criteria is fulfilled, where angle, this is the sine of this angle based on this two sources being that far apart. Okay, talked about that. Dispersion, all right. This is the fact, dispersion. I can show it again. This is what produces a rainbow. Is the fact that, again, the index of refraction for light is not exactly the same. Red does not bends the least, violet bends the most. So light, white light passing through a prism, as we've seen, will produce a spectrum. And this was discovered, that this was the nature of light by Isaac Newton and not something else. Okay. So that's dispersion. Again, red bends has a lower index refraction. Violet has a higher index refraction. It's continuous. All right. We get into diffraction. So if this is D, then the first minimum, as we see, if this is the angle, as we've been through, zoom tight, is sine theta is lambda over d. So that's there. So I'm not really going to go much into that at all. This is how spread out it is. Again, the smaller this is, the more spread out it's going to be. Because as this gets smaller, this number gets bigger. So smaller slit width, wider pattern. So I make this smaller, the pattern is going to be spread out even more. All right? And we've seen that in the lab for diffraction and interference. And then finally, the diffraction grading, which is used to analyze the diffraction grading. Which is sine theta is m lambda over d, where d, let's see if I got that right. Yep. Yep. D is the separation between, so basically you have lots and lots of slits, each one of them separated by D. So 1 over D is number of slits per centimeter, usually. So we have, like for the diffraction we may have up to 6,000 lines per centimeter is 1 over D. So in that case, D would be 1 over 6,000 centimeters. Okay? So very, very small. So that's how you get these very bright spots, as you've seen at the diffraction grading lab. And how you can analyze that. And then spectroscopy. I mean, we talked about that. Spectrum. The spectrum lab, if you have a spectrometer which has a diffraction grading, look at a source, and you get the spectrum, which is unique for each element: hydrogen, mercury, sodium, and a solar spectrum, which is, you know, the rainbow with the individual lines indicating the different materials in there. And we've gone through the hydrogen spectrum. We'll get more into the hydrogen spectrum when we talk about the Bohr model of the atom in quantum physics. All right, and I'm not going to do anything on interference in soap films or anything like that. So we're not going to do anything we call thin film interference. That's more for an advanced lab type. The only other thing here, oh yeah, forgot, is because of the wave nature of light, we'll be doing, again, polarization. I went through this, all right, the fact that light is polarized, so it passes through a slit. So if you see light coming at you here, it's like in all directions. Again, vibrating all directions it comes towards you. This is unpolarized. And then when it passes through the slit, it's polarized. And we went through the lab. Again, the lab of polarization is I naught cosine theta, where theta is the angle between two polarizers, the direction of polarization. So if you have polarized light coming in, another polarizer bent at an angle, the intensity of light coming out, again, is cosine theta squared, I should say. Can't forget that. So it's called cosine squared theta, where if they're lined up together, it's a maximum. If it's perpendicular, you get dark film. And I went through the lab, again, if you have 2 in a row or 3 in a row, what kind of interesting characteristics you can get from that. All right. And then we have polarization reflection. So again, this is the concept of polarized glasses, is the fact that light bouncing off a surface becomes polarized. And so by the fact that the light, like off of water or off of say a metal hood, the light is polarized. So by using polarized glasses, you can eliminate that glare without actually having to eliminate light. So that's a very interesting characteristic. And that is it for chapter 24. So that's a part of polarization. Again, I've gone through the lecture on that. So those are the 2 big chapters. All right, the last one is on chapter 25. So this would be telescopes, microscopes, and so on. And so, lenses. I'm not going to go into that. We're not going to do anything like f-stops or things like that with lenses. Human eye. All right, so if you're nearsighted, as we said, like I am, you use concave lenses. Okay, if you're farsighted, meaning you can see far but not near, so you use reading glasses, then you use convex lenses. Okay, I'm nearsighted, so I have a concave lens, which allows me to see farther, more focused, but I have very good close-up vision. So that's part of the human eye as far as what we have there. I'm not going to get into that, you know, how lenses work. There's also astigmatism, which is the natural, where the fact is that the nearsightedness and farsightedness is not symmetrical, but actually has changes as the light, as you move around the eye. Right? And let's see here. So telescopes, again, not going to get into this much. So again, telescopes, which I talked about. All right. Magnification is given by the focal length of the object lens, which is the main lens or mirror, divided by the focal length of the eyepiece. So again, if you have a mirror focal length, you know how long it is. If it's 200 centimeters, and if the eyepiece can be as low as, let's say, 2 centimeters, I mean, very small focal length, this is a magnification of 100 times, right? And so what you get, as we've talked about, I mean, greater magnification means smaller field of view, but it also has to deal with seeing, right? So again, this is the focal length of the main mirror or lens, and this is the focal length of the little eyepiece, which is much smaller. Okay, telescope, you know, we have reflecting, most telescopes are reflecting telescopes because they're much easier to make precisely and bigger. Let's see here. And then I'm not going to get into the microscope. I'm not going to do anything in the microscope, but there's not going to be any test questions on the microscope, but for limits of resolution, again, what we call resolving power is to be able to take something far enough away, it looks like one thing, but you get a certain distance closer, you can actually identify it as two separate light sources, which could be headlights. And this is given by the angle is 1.22 lambda over d. Okay. All right, what you've talked about there. So that's limit of resolution there. And so on. Okay, and that is it for exam 4 on chapter 23, 24, and 25 as far as this. So look at the lectures for those chapters, and this will be exam 4.